All right, James, just keep me in the frame, will you? All right, so you are aware of the fundamental theorem of calculus, the FTC, right? This is the foundation. This is the basis of calculus, all right? Integral from a to b, fx dx equals f of b minus f of a. That was relating the definite integral to anti-differentiation and talking about the area under the curve and stuff like that. So important, so huge, but there is a second theorem equal to it, which I realize is kind of a contradiction in terms. All right? Now, I know you might get a little deja vu here. That's all right. So allow me to introduce to you the second fundamental theorem of calculus. Just for the second FTC. All right. So, the second FTC relates the derivative process with the integral process all together. So, the derivative with respect to x of the integral from a to x of f of t dt. And what we'll do is, rather than me just give you the answer, we will kind of discover it very quickly in like 3 lines. So for anybody trying to think ahead here, this is saying essentially, what is the derivative of the integral of a function? Remember, I'll say what you're saying, all right? The derivative of the integral, oh my gosh. Now we're like doing like all this stuff. It's hard enough just doing derivative, then you threw the integral at me. Now you're trying to do the derivative of the integral? What? All right, well, let's see about this. So I've got brackets here, so I'm going to take care of those brackets first. So the d over dx, that just stays all by itself. Ivan, you were so generous giving us the fundamental theorem. Give it to us again. The integral from a to x of f of t dt would be?
Big F of x minus big F of a.
All right. Now, just to be clear, what these terms are, a is a constant. It's a number. X is playing the role of an independent variable here. So x is x, which means it could be anything. A is taking the place of a specific number. That being said, when we plug a into this function, we will get a specific number. Are we good on that? So I'm going to say number, or a constant. So, what is the derivative of big F of x?
Little f of x.
Little f of x. Minus the derivative of a number.
0.
0. There you go. F of x. So now let me say my thing again, and Ivan, you can complete. What is the derivative of the integral of a function?
A function.
It's a function. Ooh. Get it? The second fundamental theorem of calculus makes it 100% obvious that derivation and integration are inverse operations. Sort of like addition and subtraction. Sort of like multiplication and division. Sort of like raising something to a power and taking the root of a number. Sort of like taking the sine and taking the inverse sign. Sort of like having a function and having an inverse function. Are you getting the pattern here? Everything about math is two-sided, two-faced. Always forwards, backwards. And which one's always the hardest? Going backwards, always. Always. Everybody hates division, right? I mean, like, but I love multiplication, right? Subtraction, boo. But addition, yay, right? I mean, same thing. Derivation, we love derivation. Integration, you know. Anyway, we'll do some problems here, but this literally is maybe I can show you one. So, I mean, the way you would sort of apply this would be, what's the derivative of the integral from 5 to x of x cubed plus 2x? Oh, I guess let me put, I'll make this follow the formula even better. T cubed plus 2t dt.
Would it just be like t cubed plus 2t?
Almost. It would be x cubed plus 2x. Like that's the application of this particular problem. Okay? That's pretty good for the second fundamental theorem, and that's a lot of cases that's what you'll see. But we can extend it a little bit to make it a little bit more robust, to make it handle stuff that we don't just have an x right there. So that's what we're going to do. We're going to sort of, I guess, if this is the fundamental theorem, then these next two things I'm going to show you would be corollaries to that. All right? So here we go. The derivative with respect to x of the integral from a to g of x of f of t dt. So what I'm suggesting now is that our upper bound isn't x, it's rather a function of x, like x squared or sine x or something like that. So let's just play the game like we did over there. So we've got that. This would be the derivative with respect to x. James, what's the antiderivative from a to g of x of t dt?
F of t or f of x.
No, I'm still not hearing the right one here. Antiderivative of little f would be big F.
Oh.
Evaluated at
T.
No.
X.
Sorry, no, so wrong. Okay. G of x minus big F evaluated at A. Does that make sense now? Okay, yeah. That was the tricky one. Now, let's take the derivative of that. Now, the derivative of a function with another function inside of it is, yep, exactly, chain rule. So it's the derivative of the outside. So I'm going to write f prime with the inside intact times the derivative of the inside. So g prime of x. Like I said before in the previous example, a is a constant. So f of a, yep, that's still a constant, that's still a number. And you take the derivative of a constant, we get 0, so I'll put minus 0 right here. And big F prime is what we had called little f. So I just did this here to make everything a little clearer. So this is going to be little f evaluated at g of x times g prime of x. I guess an example of this would be, what's the derivative with respect to x of the integral from 2 to x squared of sine of t dt? if we wanted to, we could go through here, take the antiderivative, it would be cosine, right? And then, negative cosine actually. And then evaluate, and then have go from 2 to x squared, and then do cosine of x squared minus cosine of 2, and then take the derivative, so I get, but we end up with the same thing. That's going to equal this function right here, evaluated at this upper bound. Roger, you want to give that a shot?
Big F.
Well, in this case, yeah, I know, but all of these were just placeholders for these actual functions. So in this case now, sine of t is what our f of t is, okay? I'm not actually going to do the antiderivative. I'm not going to actually do the antiderivative and take the derivative. I'm going to, we did it right here, like completely symbolically, right? What I'm saying is, let's just go straight from here down to there. Yep. So it's
It'd be sine,
mm-hmm.
and then x squared it
Mm-hmm.
times a prime, or no, or
You're on there. So this is times g
yeah.
prime of x. G is upper bound here.
X squared. So then
So what is the, so this is saying the derivative,
x squared is 2x.
so it'd be 2x. Roger, if you want to, it'll just take a second. We can do the antiderivative and then take the derivative of it. Would it kind of be helpful to kind of see that process?
Yeah.
Okay, sure, let's do that. So just to make you a believer out of that, Harley, what is the antiderivative of sine of t dt?
Negative cosine t.
Yep, and we're going to evaluate that from 2 to x squared. So that would be the derivative with respect to x of negative cosine of x squared minus negative cosine of 2. Alright? Now let's apply our derivative. Ivan, what's the derivative of negative cosine x squared?
Negative sine.
Okay, so negative sine
Of x squared.
of x squared
Times 2x.
times 2x, agreed. This is minus another minus, so that's a plus. And the cosine of 2, that's just saying plug in 2 for your cosine. You're going to get some number, right? And the derivative of a number is 0.
Wouldn't you get undefined?
What's that?
Cosine 2. Wouldn't that be undefined?
Inverse cosine 2 would be undefined.
Oh.
Cosine 2, totally okay.
Oh, okay.
Alright, negative and a negative cancel each other out. So I have sine of x squared times 2x. Look familiar? So either way is fine. If you feel like doing the antiderivative and then plugging in the upper bound and plugging in the lower bound and then taking the derivative, I'm fine with that. But I'm also okay with you using that shortcut there because, hey, that's awesome. All right, so that's sort of like the first corollary, and then here we have Mr. Goddard's ultimate version of the second fundamental theorem of calculus. So that would be the derivative with respect to x. You know where I'm going here with this. The lower bound is h of x. The upper bound is g of x. The integrand is f of t dt. This is where it gets real funny. You show this to like your pre-cal friends, and they're like, "That's not math. That's like some other language."
I showed this to my mom and that's how she feels.
Yeah, and they're like, "Yes, math is a language, the universal language." Now, which symbols we use, well, we kind of decide that. What's interesting is that this is sort of like a meta math conversation, but you know, someone is like, and they would say, well, math is a universal language because we, you know, this is describing things that are beyond just like the English language and like the American experience. This is like shapes and numbers and concepts. You see what I'm saying? And someone said, well, you decided it would be d over d of x, right? And you decided that this is how you would describe the integral. So this is a result of your European background, right? Because it was the Europeans who kind of came up with this notation with Euler and all those guys, right? And Newton and Leibniz and Lagrange. Those are the ones that influence you, right? If you know, maybe if it was somebody else, it would be different notation. And that's absolutely correct. If it had been somebody else, maybe from like South America or whatever, we would be using slightly different symbols rather than Greek symbols, okay? But would the concepts be totally different? Right. So that's some fun stuff to talk about. Okay. Let's play the game here. D over d of x. So the antiderivative of little f is big F. Evaluated at the upper bound. Minus Now let's take the derivative. The derivative of f composed of g is f prime with g intact, chain rule, times g prime. Minus. You want to tell me this one?
F of h of x. Well, f prime of h of x. And h prime of x times h prime of x.
Yep. And since we're defining big F prime as little f, I'll go ahead and simplify this one more step. So it's little f of g of x times g prime of x minus little f of h of x times h prime of x. So it's literally take the lower bound, put it in there, or sorry, take the upper bound, plug it in there, then multiply it by its derivative, minus take the lower bound, plug it in there, multiply it by its derivative. That is the second fundamental theorem of calculus. Before I give you your homework, let's see, talk to me about next week. Anybody plan on being gone these days?
Friday.
Thursday we have our senior breakfast. Wednesday's awards day. I don't know if that affects in the morning or
Oh,
not.
that is in the morning. Yeah. And then Fridays. what is it?
Black House.
Anybody in Black House?
Yeah.
In James. Okay. So party.
Wednesdays in the
No, Thursday's senior breakfast. Wednesday's awards day.
I think that starts at 10 o'clock.
Oh, no.
Awards program is at 10 o'clock. So, state golf is Monday, Tuesday.
I just wasn't sure what time it was on Wednesday.
All right. And then this following Monday,
We have final.
senior odd finals, and then Tuesday is even finals.
Mm-hmm. Wow, we're almost
Bro.
done.
Odd and even.
We'll go
Okay.
to all of our classes though, right? Monday and Tuesday.
I believe you will, and that's good that you're going to go there because we'll have a review.
Alright, awesome.
probably of some type. Okay, so then here, this is going to be our exam.
It's, those two are full days, and then we have Wednesday
And then this is a half day.
Thursday that are half days, but we're going to go practice.
Right, y'all will not probably be here during those days. I'm not sure what exactly you're doing. I mean, I could tell you.
We're practicing for our baccalaureate and for the walk for graduation.
Yeah. Graduation practice at 9 a.m. on Wednesday.
It is.
I don't know what you're doing on Thursday morning. Maybe just sleeping in.
We have a breakfast, I think, and then we come eat breakfast, and we all leave.
Okay. Let's see here. So as far as I'm concerned, I mean, yeah, these two classes, this is going to be for Ivan and maybe Gracie if she's here. This day would just be sort of like what I'll try to do is I'll try to give you the review on Wednesday.
I might not go Friday, depending, because I want to review for my finals,
Mm-hmm.
and that's more important than going to
Yeah.
our party thing.
Well, I'll give you the review I'll try to give you the review on Wednesday. That way you'll have it, and then we'll go over the answers on Monday. Okay. Your exam will be multiple choice. Okay, so we're looking at Monday, Tuesday, Wednesday as our last 3 instruction days. Then we've got a question now. Yeah, it would be good to have one more quiz, but maybe we'll have like I don't know. If we do have a quiz, it'll be like a take-home quiz or something like that, or maybe just a very brief quiz on this day or something. I don't know. It's too early to have it on Monday or Tuesday. We'll do something like that. As far as I'm concerned, what we need to talk about, the only other things I want to make sure that you're aware of are some applications of integrals, okay? So definitely motion with integrals. Something called the mean value theorem, and as it relates also to the average value theorem, and volume and surface area. Those are the big things that normally Calc 1 kind of hits on if you get, it's traditionally part of that. And I think y'all did discuss a little bit of volume and surface area in the fall, right? Just a touch.
So.
We'll look at it and literally we'll kind of see some stuff. We've got some graphics and things like that, and you'll be like, oh my gosh, it's awesome. I can totally see the use of the integral. So we'll probably talk about those 3 things on those 3 days. Maybe give you a take-home, maybe like the review would be like a take-home quiz type thing. Speaking of which, before we go, I have papers to give you along with your quiz if you, that we took earlier. I think we took the end of last week, so on hand I created. Okay, let me give you this homework. This copy machine, this 3-hole punches are not doing too great. Let's go ahead and pick 1 or 2 of them. Oh, you can see that. I'll let y'all pick the problem. Rigel's going straight to the back. What do you want? What do you want, Rigel? What you choose?
17.
All right. So read those instructions to us, Rigel.
Okay. F of x equals the integral of negative e to the t plus 3 and dt.
From x to x squared.
Yeah, from x to x squared.
What do we need to find?
The derivative
Mm-hmm.
of this whole thing.
Right. So maybe if you want to write something on, so they want us to find the derivative with respect to x of the integral from x to x squared of negative e to the t plus 3 dt. Are you comfortable using the second fundamental theorem of calculus?
Yeah.
Let's do it. So we said that it's going to be, so this is, let's be clear, that's our function, L of t, that's g, and that's h, right? So we said the derivative of the integral from a lower bound to upper bound is going to be the function. So negative e to the t plus 3, whoops, hold on, but evaluated at the upper bound. So every time I see a t, I'm going to write x squared. So x squared plus 3 times the derivative of g of x. The derivative of x squared is
2x.
minus the function evaluated at the lower bound. So negative e. Every time I see a t, I'm going to replace that with x. So x plus 3 times the derivative of lower bound. And this is a terrible problem. I should have chosen something a little bit better, but that's okay because the derivative of x is
1.
1. So normally we kind of like to write everything else before the e, so I'm going to write this as negative 2x e to the x squared plus 3 minus a minus turns into a positive e to the x plus 3. Anything look incorrect on that to y'all? James? Looks good, James? Negative 2x e to the x squared plus 3 plus e to the x plus 3. I wonder, would it be possible to combine those? Ivan says no. Why not, Ivan?
Because the exponents are different.
Yeah, exponent's different.
And because
Plus-
it's addition.
Yeah, it's addition, not multiplication. And because we got 2x there. So yeah, totally unlike terms. Good choice there, Rigel. Alright, let's pick one more, then I'll call it quits for today. Harley, how about you? Which one do you want us to look at?
I'm just gonna shoot out a number,
Do it.
like 8. Yes.
Alright then. So what they're wanting us to solve is the derivative. So that'd be the derivative with respect to x of the integral from negative 3 to x squared t squared plus 8t plus 11 dt. Now, if y'all feel the most comfortable doing the integral, then plugging in the upper bound and lower bound and taking the derivative, you go ahead and do that. But I say, why bother, right, James?
Sure.
Let's just use the second fundamental theorem of calculus. So the second fundamental theorem of calculus says take that upper bound and plug it in every time you see a t. The derivative of the integral of this function is function evaluated at that upper bound. So every time I see a t, I'm going to replace it with parentheses x squared. So parentheses x squared squared plus 8 parentheses x squared plus 11. That's the function evaluated at the upper bound times the derivative of the upper bound. So 2x minus, well, it's not going to be minus anything because this is a number, right?
The derivative is supposed to be 0.
Yeah, so the derivative, so when I do this, take the integral and put, yeah, so that turned out to be 0. So yeah, so we don't need that. So can you do two things at once? X squared squared is times 2x, which gets distributed here across all three terms. 2x to the 5th plus 8 times 2 is 16, x times x squared is x cubed, plus 22x. 2x fifth plus 16x cubed, yep. Alright. I think y'all can definitely take care of this. Get rock solid on the second fundamental theorem of calculus. And see you next week. James?